Today we are going to take a look at motion graphs. So for motion graphs, we looked at this on Wednesday and Thursday of last week with the gizmo. Motion graphs are important for us because it lets us show the relationship between position, speed, and we know interchangeably with velocity, and then time as well. So it's a nice way of just graphically representing how those things relate to each other. So it lets us easily see how that speed or how that position changes over time. We have a fancy name for them. They're called kinematic graphs. So it could be position versus time graphs or speed versus time graphs. And for right now, speed versus time graphs is what I'm calling it. The formal term for it is velocity versus time graphs because, again, for that one, just direction does matter. So for a position versus time graph, it gives an object's position based on a given time. The position is the y value, the y-axis, so the vertical axis tells us how far it's gone, and the x-axis tells us how long it took to get there. If we were going to actually try and graph some data here, suppose that we're helping someone who's training for a track meet. We want to know that she's running at a constant speed, so we mark out 50-meter increments and measure her time between each of those intervals. So you can see after 10 seconds, she's gone 50 meters, after 20 seconds, she's gone 100 meters, and after 30 seconds, she's gone 150 meters. So if we were to create a position time graph with that data, it would look something like what's down there at the bottom. You can see that we're just tracking each of those increments, and we can see that after we plot all four of those points, it does look like her speed is constant. To actually find her speed, we would choose any point and divide the distance by the time. Since here it is a constant speed, it's just a linear graph. So no matter which point we chose it at, we could just divide, distance by time, which is what we're doing here on this next slide. So at 50 meters, it took her 10 seconds. That's 5 meters per second. At 100 meters, that took her 20 seconds. 5 meters per second, what that reduces to. So that's just showing that she has a constant speed. She's not slowing up, or she's not slowing down or speeding up. For this next one, if we're going to graph the motion of this car, here again we're just kind of collecting points in a different way. Here you can see I've already taken those points and turned them into coordinates. And if we were going to graph this, it should look something like this. Obviously, how you graph it and the coordinates that you use are going to be the same, but the formatting of it is going to be up to you on whether you want to do it as just an XY axis, whether you have the grid in there or not, but that's what that is. So what's the car's velocity? Here again, we can take any of those two since it's a constant. It's just a flat, regular slope. It's a linear equation, so we would just find the slope of that line. Here we can just do it easily by taking position divided by time. So 10 meters per second. What does slope have to do with it? Well, slope, as we saw, we know slope is the ratio of rise over run. So it's our change in our y-axis over our change in x-axis, which, since we're talking about a position graph, the y value is how far I'm going, the x value is how long it took me to get there. So if I was in talking about this, the steeper your line is, the bigger your slope. That means there's more distance that's traveled in that same amount of time. So a steeper line means that we're traveling faster. A less steep line means we're traveling slower. So here you can see the car animation-wise. The blue car and the red car both have a constant speed, but since the blue car is moving much slower, it has a less steep line. You can also see here that the red car doesn't show up until 4 seconds into, if we call this a race. So you can see position-wise, it starts right there at 4 seconds. And that's just going to kind of emphasizing that. Negative slopes. So we know that our position is our y-axis. So if we're moving down, that means that we're moving backwards in our position. It doesn't necessarily mean we're walking backwards, we're just losing value in our position. So in this, it really depends on kind of how you're considering zero or what you're considering for your position. But whatever you're considering kind of the starting line, if you're going towards that starting line instead of away from it, that would mean you're moving backwards. Because if we're talking about our starting line, we gain value in our position that's going away from it, like a regular race would. So if we have any time in our graph where we're moving towards that starting line instead of away from it, that's just going to give us a backwards motion, which would give us a negative slope. So this, and I'm going to come back to this as well, the position one is what I wanted to emphasize here. As we're moving forward, our slope is going to be positive. If we're moving backward, our slope is negative. Velocity-wise, we'll talk about that in a second, but going to kind of the next level from velocity, if we have a positive slope, we're accelerating, so we're gaining speed. And if we have a negative slope, we're going to be decelerating, so we're going to be losing speed. So just looking at this graph, we've got a couple of different examples of unique things that kind of the shape of your graph tell you. You can see from the green graph, it's a fast, steady speed because it's just a straight line, and it's got a nice steep slope, so we're moving quickly. For the red graph, we've got something a little bit different happening because we have a steady speed at first, and then you can see where it kind of flattens out and hits that plateau. We're not gaining any distance, we're not losing any distance, we're still going through time, so I'm still going to continue moving in the x direction, but my y value just stays constant, which means we're standing still, we're stationary. And then you can see towards the end of that red graph, we start with a negative slope, which means we walk back toward the start line, or wherever the starting position is. The blue one, this is for a position time graph, which sometimes I can call a distance time graph. You can see that my blue graph is curved. That means I am still moving forward. I do have a positive velocity. But you can see that curve tells me that my speed is not constant. That rate is not constant. It's increasing as I go along. So that shows me for a position time graph, if I have a curve, that means I'm going to be accelerating. We're going to skip through that. Prediction-wise, you can kind of create some stories or some context to these different graphs, and that's going to be something that you have to try and figure out. If I tell you what this graph, basically means, then you should be able to tell me a description of, what might be happening. So here, if I'm telling you this is the motion of a car, you could say, all right, well, for the first 5 seconds, the car is moving at a positive velocity of 5 meters per second, and then it stops and stays there for the next 5 seconds. The straight line doesn't, not the straight line. Straight line just means a constant velocity. What it should say here is a horizontal line means the position is not changing. So in this case, the car would be stopped for those 5 seconds. So speed versus time graphs, those are, again, velocity time graphs. Very similar. My y-axis here is my velocity or my speed. My x-axis is still time. So in this case, it tells me how my velocity is changing or how my speed is changing over time. That's huge. All right, here we go. All right, so this graph shows a ball rolling down at a constant speed on a level floor. On a speed versus time graph, constant speed is shown with a horizontal straight line. So again, here, kind of like what we were saying before with position time graphs, if it's not moving, the position is not changing, so it's just a horizontal line. Here, when I have a constant speed, so my velocity isn't changing, that's going to be a horizontal line. That doesn't necessarily mean that my ball is sitting still. In this case, it's rolling at a constant velocity. In this case, it's a constant velocity of 1 meter per second. So if we compared that to its position graph, so these two graphs at the bottom, this is for the same scenario, so a ball rolling on the floor at a constant rate. You can see that my position time graph is an angled line, but it's a straight line, and it's a constant velocity. It's a constant position change for every second. But you can see my speed versus time graph is a horizontal line, and that's because, again, my speed isn't changing, but I am still moving. So they look very different, but they really mean the same thing, and that's why it's going to be really important for you guys to be able to identify which of those two types of graph we're dealing with. So in this one, if we're going to try and graph this, the context we're given, Maria walked at a constant speed of 6 meters per second for 5 seconds. Then she runs at a constant speed of 10 meters per second for 5 seconds. So she starts off walking, or jogging maybe, and then she sets off into a run. If we were asked to create a speed time graph using her data, the speed versus time graph we are going to be creating for the first 5 seconds, we can see that she's running at 6 meters per second, and then all of a sudden she jumps up to the second set of 5 seconds, from 5 until 10. We have a speed of 10 meters per second. Now, this jump here is probably a little more unrealistic, where we don't have, we know no human being alive or ever has existed that's able to immediately change their velocity from 6 meters per second to 10 meters per second. This, in actuality, would have to be just a steep curve and then leveling off at 10 meters per second, because we know that we can't instantly change our speed from 6 to 10. But just in practice, kind of an ideal world, we can just use this kind of step graph. Alright, speed versus time graph. Changing speeds. As we know, most objects don't move at a constant speed. So if our speed versus time graph has a slope, when it slopes up, that speed is increasing. And when it slopes down, that speed is decreasing. So that's where we're talking about that acceleration versus deceleration. And if the graph is horizontal, we were talking about that. My object is moving at a constant speed. So we can see here these 3 people, Albert, Bob, and Charlie. All 3 of them are moving. So this is my distance time graph. Putting this all together, distance time graph. So they're all gaining distance. We're all moving towards the finish line from the start line. But we can see they're happening at different rates. So we're asked to identify which runner won the race. We should be able to identify that Albert won the race, because in time, if we're looking at the x-axis here, Albert got to that 100 meters before Bob and Charlie did. He finished the race in 12 seconds, Bob in 14, and then Charlie in about 17 seconds. Which runner stopped for a rest? We can see here, since this is a position time graph, this little spot in the middle here where it's flat, Charlie took a break. He was starting off nice and strong, and all of a sudden 8 seconds hit and he got really winded and had to stop and catch his breath. And then about after 13 seconds, then he could take off and run again. So Charlie is the one in this case that stopped for a rest at the 50-meter mark, so halfway through the race. How long did he stop for? Well, he stopped at 8 seconds, and then he started taking off at 13 seconds. So 8 minus 13 means he was there for 5 seconds. If we looked at the next question here, same graph, still distance versus time. How long did it take Bob to complete the race? Well, again, Bob gets to the 100-meter mark here at 14 seconds. If we were going to calculate Albert's average speed, so we can see here, kind of like what we talked about with our Physics 500 that we did, when we were going through and doing our calculations, we couldn't find the actual speed that we were traveling. It was an average of those distances, or average of those speeds. And that's going to be the case anytime you don't have a constant velocity. So you can see here, like for Charlie, from 0 to 8 seconds, this is a pretty flat line. So we could find the slope there and know exactly what that slope was and what that rate was that he was running at. But for Albert, since this is curved, the best we can do is find an average of his speed, because it's going to be different depending on what interval we're talking about. So for this, the way that we would handle this, since we know speed is just distance divided by time, we'll just look at his average speed over the entire race, which he did the race 100 meters in 12 seconds. So if we divided those numbers, we would get 8.3 meters per second. That's all I got for you today. If you have any questions, just make sure you come ready with those for class tomorrow. But otherwise, have a fantastic day.